I'll talk about our big data analytics project, tip prediction and GPS noise modeling on New York City taxi dataset. This is the overview of our analysis. We did two analyses in two different areas, Upper West Side and Midtown. We used 11 GB of taxi trip data and two sets listed here, including Hadoop and Spark. The first analysis is about tip prediction, and the second analysis is about GPS noise modeling. We used random forest for the first analysis and Gaussian mixture model for the second analysis. The main results are 77% accuracy in binary classification and numerical criteria for possible GPS correction. About datasets, we decided to use half-year subset of taxi trip dataset from January to June this year, 70 million rows in total. It contains pickup drop-off longitude and latitude with time, fare and the amount of tip, and several flags like rush hour or not, airport fare rate, and so on. We built a Spark cluster consisting of 3 nodes. The first analysis is about tip prediction in Upper West Side. Previous research used the exact amount of tips as their objective variables. But actually, from taxi drivers' perspective, it's more useful to use how much tips they earn for a particular time interval as an objective variables. Following the driver's perspective, we use hourly tips as our objective variables and formalize this as a binary classification problem. We defined this variable is high, whether each trip is worth more than $12 tips per hour or not. $12 is the median of 20% tip rate requires. This novel objective variable can highlight a different aspect of the trip amount problem. When you look at the areas with high average amount of tips, Midtown and Wall Street would appear as the highest areas. But when we colorize areas according to the hourly amount of tips, the real lucrative areas are not Midtown and Wall Street, but Upper West Side and Upper East Side. And what's nice about hourly tips is that it has a potential business application. For the sake of fairness, taxi companies can assign areas of taxi drivers if the ratio of lucrative trips are so different between areas. You might think that the objective variable we defined is high is too arbitrary to be justified. But it actually sheds light on some transportation patterns in New York City. X-axis is time, from May 1st to 31st. Y-axis is the ratio of two different types of trips. This clearly shows whether trips will be worth $12 highly depends on the time slot. During 8 p.m. to 1 a.m., 75% of trips are is high equals 1. And some peaks have different heights, like this or this, usually weekends. This pattern is hard to capture just by absolute tip amounts. So we incorporated a weekend flag and a time slot as features of our model. We built 3 different random forest models by Spark live. The baseline accuracy is 51.5% when predicting all trip records as is high equals 1. If we use all of these 11 variables as features, this random forest achieves 77% of accuracy against 1 million test data. And when before writing, only 5 variables can be used, and accuracy goes down to 59.5%. This means that only 80% of trips with more than $12 hourly tips can be predicted before writing, and implies that no need to take some actions for correcting the area assignment. The second analysis is about GPS noise in Midtown. Even though the actual streets are like square grids, recorded location data is not in Midtown area, maybe because of high buildings like skyscrapers. So a question arises, can we estimate true GPS locations from this noisy data? If possible, that's beneficial for any people using GPS in Midtown area. Tourists can be navigated into their destinations. Ride-sharing companies can exactly locate drivers and passengers, and so on. First, we tried in the area easy to model. For example, this area contains 14 horizontal streets, much like a Gaussian distribution. A previous paper used Gaussian mixture models to estimate the number of lanes from car GPS trajectory, and GMM can actually estimate streets information fairly well. Then how about this area? Can Gaussian mixture model estimate streets in this noisy area too? Well, actually, naively applying GMM failed. Some of the Gaussians are too wide and do not represent streets. One of the reasons we failed is this setting in New York City is too different from the setting in textbook. In textbook, usually the number of clusters, k, is determined by cross-validation, and the means are randomly initialized because of no knowledge about true means, and variances for each Gaussian are not constrained. But we can incorporate background knowledge into GMM. We already know that k is equal to 14. True means are just street centers, and all of the 14 Gaussians must have equal variance because they are recorded in the same GPS devices. And we found out that GMM with constraints works pretty well. By constraints, we mean initial means are aligned in equal interval, and one variance is shared for all 14 clusters. The red horizontal lines in this figure is the estimated means. They really go through the street centers. This means that even though the raw data are very messy, and a human can't see 14 clusters in it, but it actually preserves some information about tree street membership. This small peak is captured by one Gaussian, and interestingly, these two Gaussians, which have their largest overlapping areas, are of 49 to 50 Street, where Rockefeller Center locates between the horizontal streets. There is a small vertical road here, and GMM can detect this kind of bias too. In summary, we did two analyses. In the first analysis, we proposed that no very objective variable is high, whether hourly tips are over $12 or not. We confirmed that is high captured traffic volume pattern and achieved 77% accuracy by random forest with full features. In the second analysis, we demonstrated constrained GMM works well, and the return probabilities for true street membership in midterm can be used as a useful criterion. Next steps are more features for prediction and other area investigation. I'll talk about our GitHub repository for future repository users. Basically, we did preliminary analysis by R language and did production analysis by Python and Spark. In order to define all variables in R scripts, you have to build first a PostgreSQL database for taxi trip data by this guy's script. So it will take a few days even if you just selected subsets of taxi database. Looking back, I think we don't have to use his database because our production analysis just preprocesses the dataset from the original CSV files. You could think of a way to define datasets for R from the original CSV files. It could be a much faster way to execute our scripts. So I'll talk about some aspects of our R scripts. First, initialization codes are in this advent.r, and second, most of our scripts use dplyr and TDR for data preprocessing. So if you don't know how to read codes written by these libraries, I recommend reading their manuals. And third, most of our preliminary analysis results are stored in EDA directory, exploratory data analysis. So I don't think you need to execute our R scripts for checking how we investigated data. So rather, you can just check each file here. And our Spark script is comprised of two parts, a few of IPS notebook files, and a Python script. So this Python script is converted from the IPS notebook file and can be executed by Spark submit command. And the Spark submit results is recorded in these text files. So you could check some metrics for binary classifications here. One unique thing we did in this IPS notebook is maybe we did coordinated transformation by PyProj libraries here. So PyProj library is a map projection library, and it transforms raw longitude and latitude data into Cartesian x and y, and it's highly useful for visualization and Gaussian mixture models. So you can see that these low longitude and latitude data is transformed into much horizontal or vertical maps, which is quite useful.